All righty. So at this point, we are recording. You should be able to see that on your end. And here we go. All right. So this was assignment 2. This was due tomorrow. This was the assignment that was due for today. Hopefully that you were able to do most of it. So let's take a look at it. All right. So question 1, the scores for a reference population on this IQ test are approximately normally distributed with a mean of 100 and a standard deviation of 15. So first question, what score would represent the 50th percentile? So in a normal distribution, which looks like this, the number in the middle is always the mean, which in this case is 100. And that number is always at the 50th percentile. There's 50% of the area below the mean. So if you're at a certain percentile, what that's telling us is you're better than 50% of the people who took that test. So in this case, a score of 100 is the answer to part A. Okay. Part B. Part B, yeah. In what range would, or I should say a score in what range would represent the top 1% of scores? Okay. So part B is sort of like saying, I think we talked about this last time. There's this group called Mensa, which is this group of people that have high IQs. Usually it's the top 2% of the population or something. So if you're in the top 1%, like question B is saying, then we go over here, we mark off, I'm going to put some number X. I'm going to do that. I don't know what this number really is. Okay. But I'm going to shade in that number. Okay. Let me just see one thing here for a second. Good. Just making sure I'm screen sharing. Everybody can see things. I don't know what IQ I need to be in the top 1%, but what I do know is that the area here is 0.01 or 1%. Okay. So here's going to be our plan. We know a z-score is X minus the mean divided by the standard deviation. In our case, X is unknown. The mean is 100. The standard deviation is 15. And even though you don't have the z-score, I claim that we can find it. So we can actually figure out what z-score goes here. And here's how we're going to do it. If 0.01 or 1% of the area is above this number X, that means that 99% of the area is below it or to the left. So this area to the left is 99. So this is going to be our plan. What we're going to do is we're going to go look up something on a normal distribution table. So we'll do this here. Okay. So I'm going to go to a normal distribution table. And remember, in this question that we're working on, we really have the area of 0.99. And so I want to find the z-score that captures an area of 0.99 to the left. So that's my plan. So if I go here, I'm just going to take a screenshot of this for a second. Bear with me for a minute. It's a little laggy. That lagged out on me in an unhap that did not make me happy. Hold on a second here. All right, so this looks good. I'll send this to a smart notebook. And what I want to do now is find an area as close as I can to 0.99. And I'm flexible with this, but I think the one that looks good is right here. That's 0.9901. And what you notice is that the z-score that goes with that, if I go out over here, I get 2.3. And if I go up to the top, I get 0.3. So that means z equals 2.33. That's the number that would capture an area of 0.9901 to the left. So what that means is that this z-score here is 0.99. Oh, no, I'm sorry. 2.33. Oops, probably a little bit of a brain malfunction there. Thank you. Sorry about that. So this is going to be 2.33. So here we go. 2.33 equals X minus the mean over the standard deviation. And now we can solve backwards for x. Okay. If you have any questions, you can always just, unmute yourself and ask me. But the whole key in this question is, since we have the area, the top 1%, we have to go backwards and figure out the z-score and then solve for x. Way to solve this is from the old days. We'll put this over 1. You can cross multiply if you like. So like 1 times the x minus 100 is x minus 100 equals 2.33 times 15. X equals 100 plus 2.33 times 15. So if we take a minute and type that in, I'll type that into the calculator for you. 100 plus 2.33 times 15. And I am getting x equals 134.95 or 135. So at least according to this data, if your IQ is 135 or higher, you'd be in the top 1% of people, or people's IQs. Okay. All right, good. So that takes care of that. Let's look at the next question. There was another question underneath there. It's kind of hidden now. Let me just highlight it for you so you don't miss it. They said, what proportion of the population has scores below 110? So let me add a page. And so we want to be below 110. Ooh, that's not what I wanted to do. Sorry about that. Let's go back to pen mode. So here's our normal distribution. We know the mean of 100 is in the middle. 110 is over here somewhere. And we want to know what percent of people are less than or equal to that. Okay. So in this case, notice we want the area. So if you want the area, you're going to have to go find a z-score. So z equals 110 minus the mean of 100 over 15. Or z equals 10 over 15, which, if I'm dividing correctly today, I think is 0.666, like forever. Really, it's going to be z equals 0.67. So we're going to go back to that normal distribution chart and try and find that z-score. So here's the normal distribution chart. Let me make a copy of part of it for us. Okay, that didn't work the way I wanted. Sorry about that. A little bit slow. So I don't know why it's waiting for that to do it. If you looked in the chart, you would see an area of, hold on a minute, 0.67. I'm getting 0.7486. So it looks like this area over here is 0.7486. I looked in the body of the chart to get that number. I took an image and it just kind of disappeared, so I'm not sure where it went. So that's the answer to part C, 0.7486. If you'd like to express it as a, that's weird, express it as a percentage, you could do that. You could say like 74.8% or something. Okay. All right, so we did that question. Part D, what proportion of the populations are of the scores are between 180 and 110? So this you have to be a little bit creative with for part D. So between 80 and 110 they want. So here's our normal distribution. We mark off 100 in the middle. We mark off 110 over here and 80 over here. And we want the area between those two numbers. Now the problem, of course, is that the chart only works by giving you area to the left of a number, and that's it. So in the previous example, in part C, we just figured out that the area below, so all that blue area, we just figured out was 0.7486. All right. So what we're going to do next is we're going to do a z-score for 80. So the z-score for 80 is going to be 80 minus 100 over 15, or negative 20 over 15. So if we divide that, right? Okay, hold on a second. You get negative 1.33. It's really threes forever. You really only need 2 decimal places to use the chart. Now let's try and use this chart again. Hope that it doesn't malfunction on me. Okay. So I know I'm going to want a z-score of negative 1.33. So here we go. Put a picture of my now. Okay, that worked finally. That was good. So I'm going to start at negative 1.303. I'm going to go down and over. And I'm getting an area right here, 0.0918. That's the area to the left of that z-score. So that tells us that this area here is 0.0913. Okay, so keep in mind, we want this green area that's in between 80 and 110. We know that the area to the left of 110 is 0.7486. We know the area to the left of 80 is 0.0913. So we can do 0.7486 minus 0.0913 and get the area we really want. So 0.7486 minus 0.0913 gives 0.6573. And that's your answer right there, 0.6573. Okay, so that problem, you're just taking 2 areas and subtracting them to get the area in between the numbers. Okay, let's see. There was one more question there. What is the interquartile range? I'm just going to tell you to skip that. Okay, for the purposes. Well, actually, you know what? I'll just do it. Don't worry about it. Let's just do it. It's not a big deal. IQR, interquartile range, by definition, is Q3 minus Q1. So Q3 is the 3rd quartile. What that means is that in the normal distribution, there's some number over here. I don't know what it is, X. And I know that the area below it is 75% or 0.75. So let's see if we can figure that out. So first off, I would like to get the z-score. So we'll go back. You go back to the table again, and you would do the following. So I guess I'll demonstrate this, make sure we're good. I'm looking for an area as close as possible to 0.75. So I'm going to do this and send it to a page. And if I look in the body of the chart here, I think I see this number, 0.7486 or 0.7517. Either one of those is pretty close. Technically, the first number is closer, but I don't care. I would take either one. This goes with 0.067. So Z equals 0.67. If you took 0.68, if you picked the next one, I would be okay with it. So that said, back over here. So now we know that Z is 0.67. So we'll set up a little equation. 0.67 equals X minus 100 over 15. And if you solve that, here's what's going to happen. You'll cross multiply. It's like we did before. So you'll get 0.67 times 15 equals X minus 100, add 100. So you get 100 plus 0.67 times 15 is equal to X. So we do that math for you. Plus 0.67 times 15, and I am getting 110.05. So this X value, oops, sorry about screen jumping there, is 110.05. Okay, so I'll save you a little bit of time. There's 100 in the middle. Over here, there'd be another number, X, where the area below that number would be 0.25, because that's the lower quartile, right? It's 25% of the area is below that number. If you take the time to look up the z-score that goes with that, surprisingly, or maybe not, you get negative 0.67, which is sort of the same z-score we had before, but negative. So you have to solve a different equation. So negative 0.67 equals X minus 100 over 15. And we're going to cross multiply there. We do the math correctly for this problem and solve it. you will get 89.95. So this will end up being 89.95. So let me just highlight the important numbers then. This is Q1, 89.95. This is Q3, 110.05. You ready? What color am I going to use? I guess I'll use black. IQR equals 110.05 minus 89.95. So if we do that math, we get minus that, and we getting 20.1 is your interquartile range. Okay, so that takes care of that first problem with the normal distribution. Okay, let's look at the second page. Number 2, raw scores on a behavioral tests are often transformed for easier comparison. A test of reading ability has a mean of 75 and a standard deviation of 10 when given to third graders. So let's make a little note of that. So for third graders, the mean is 75 and the standard deviation is 10. Sixth graders, so if you're a sixth grader taking this test, I guess, the mean is higher, it's an 82, and the standard deviation also seems to be bigger, it's 11. Problem saying, calculate the z-score for each student. So we have this kid, David, who got a 78 on the test, but David's in third grade. So Dave, the z-score is 78 minus 75 over 10. And that's going to be 3 over 10, or 0.3. We have this person, Nancy, who got an 81. So for Nancy, the z-score is going to be 81 minus 86 over 11. So we do a little math there, 81 minus 86 divided by 11. In that case, I'm getting negative 0.45. Okay. So then the question is, who scored higher within his or her grade? That's what they're asking, right? That's the question. So if you think about it, David, his z-score is positive. He was 0.3 above the mean, 0.3 standard deviations above the mean. Nancy's z-score is negative, so Nancy's below the mean. Then, so in this case, what it means is that Dave did better than Nancy. It might seem strange to you because Dave's score is only a 78, but compared to other third graders, Dave was above the mean. And Nancy got an 81, but compared to other sixth graders, Nancy was below the mean. So that's why you see this. That's why you say Dave is greater than Nancy. All right, second question, convert. They're saying the distributions are normal and then determine the percentiles. So for Dave, his z-score was 0.3. For Nancy, the z-score was negative 0.45. Let's get the percentile. So go back to the chart here. We're on positive z-scores here. So remember, area to the left is a percentile. That's what that fundamentally is. Okay, so it lagged out on me. Hold on a second here. Yeah, that was helpful. Okay, let's do that again. Here we go. Sorry about that. So here we go. We're looking for a z-score of 0.3. That z-score is right here. Here's 0.30. You get 0.6179. So that means that David is at the 61.79 percentile. Let's go look up Nancy now. So for Nancy, we're going to do this. We'll go over here because Nancy had a negative z-score. So we'll do that. And drag this out. Here we go. And go back. So now I'm looking for something as close as possible. Well, I'm just looking for negative 0.45. That's what I'm looking for. Sorry. So negative 0.4 and then 5. This is 0, 0.01, 0.02, 0.03, 0.04, 0.05. Here's 0.05. Here's negative 0.4. We go across. We get 0.3264. Sorry about that. So Nancy is 3264, so 32.64%. So if you're going to interpret your results here, what you would say is, I'm just going to say it, I'm not going to write it, but for David was better than 61.79% of other third graders. Nancy was only better than 32.64% of sixth graders. So while Nancy has the higher numerical score of 81 compared to other sixth graders, Nancy's only as good as the lower 32%. David had a lower score on the test, but compared to other third graders, David was better than 61% of third graders. So that's how you make comparisons between different distributions. Okay, these problems will go a little bit more quickly, I think. The bar graph at the right shows the distribution of religious affiliation around the world, which the following statements best describes what's wrong with the graph. Okay, so since this bar graph, the bars should be touching each other. That does not have to happen. The bars can touch each other or not. The other category should be subdivided into all religions, into all the religions included. That is a possible, I'm going to put a question mark next to that. That might make it better. Now, I don't know a lot about different religions around the world, but my guess is there's quite a few of them. And so maybe if you were going to try and take this bar and separate it, you'd end up with a ton of little bars that you can barely see the height of. So that might have been the reason why whoever made this chart decided to combine those. C, the bars should be in decreasing size order. It actually doesn't matter. It might be nice, but it's not necessary. You know, we can clearly see here, according to this survey, when these people, this group of people asked, being Christian was the highest percentage in this particular group of people. But who's to say? I don't think that's true worldwide. So I don't know where this information was collected from, but I think there are religions that are, I guess, more popular than Christianity. We'll say it that way. Part D, the starting the vertical axis of 5 distorts the relative frequency of the religions. That's exactly right. The problem with this is because you started at 5, right? So let's say you take a look at, like, say we're going to compare Hindu to Buddhist. When I look at these two bars, it looks like you could fit, let's take the Buddhist graph for a minute. It's about this high. I think we could fit about 4 of them into the Hindu graph. But in reality, if we look at the graphs and the information, it looks like Hindu is about 15%. And Buddhism looks like it's about 7.5%, which means that the Buddhist bar should be half the height of the Hindu bar, and it's not. So this graph is misleading us into thinking that certain religions are much more popular than others, when in fact that's not true. Okay. All right, let's keep going. Number 4, the cumulative relative frequency graph at the right shows the distribution of lifespans for 39 US presidents. Which of the following is closest to the 70th percentile? Okay, so 70th percentile, you look on the side, this is fancy word. It says, I'll highlight it for you. Right here, it says cumulative relative frequency. That just means percent. So all that's saying is it's like the percentile. That's all that is. So we go over here, we mark off 0.7, we go across, and we go down. And it looks like the number we would get there is 75, or about. The closest number on here to that is choice D, 77. So while it's not perfect, maybe I could have done a better job. I mean, it looks like maybe I could have gone up a little bit more and gone over a little bit more, would have been better, 0.77. So that's okay. If you were doing a problem like this for me on your midterm, and you're nervous about, like, you know, is Dr. DeMarino's going to be super nitpicky? Don't worry about it. Just draw this picture. If I see this picture, and let's say just because of the way you drew it, you did something like this, and you thought 70 was the answer. If I can see those lines, you're going to get full credit for it. All right, let's look at the next one. Number 5, the customer service department of an online store keeps track of the length of time customers wait on hold for a representative. The mean wait time is 5 minutes. So the mean of X is 5. And the standard deviation of X is 2.3. Okay, so then they make this new variable. They say a bunch of things here, but the bottom line is this is new variable Y that they're giving us. And the question is saying, what's the mean of Y and what's the standard deviation of Y? Okay, so please keep in mind that mean measures the center of data and standard deviation measures the spread of data. Like in other words, is the data close together or is it very spread out? And they're asking us in this question, what's the mean and standard deviation of Y? And we're supposed to pick that from the choices below. All right, so let's go to a new page and let's just investigate something. Suppose they gave you the numbers. Ooh, my screen wigged out, sorry. So give you the numbers 1, 2, 3, 4, and 5. Now the mean of that list is 5, and the standard deviation of that list is about it's about 1 point, I think it's about 1.5 or 1.6, something like that. We'll just pretend it's 1.5 for now. Okay, so if I were to take all the numbers and let's say I increased them all by 3, the new list would become 4, 5, 6, 7, 8. So notice in this new list, the mean is now 6. It's 3 higher than it was before because I made every number exactly 3 higher than it used to be. The standard deviation, though, is still 1.5 because the actual distance between these numbers didn't change. Notice all these numbers are 1 unit apart. And the same thing is true here. So what that's telling me is that the mean is affected by addition, but the standard deviation is not. Okay, let's take that same list of numbers again. So 1, 2, 3, 4, and 5. And let's take the whole list. And let's say we decide that we're going to multiply that list by 4. If we do that, we get 4, 8, 12. Sorry, that should have been 16. My bad. 16 and 20. And so you can tell now the old mean was like it was before 3. The old standard deviation is now 1.5. In this new list, though, the new mean is 12. So notice the mean went from 3 to 12. It got multiplied by 4. The standard deviation has to be bigger. And here's why it has to be bigger. Ready? These numbers started out, they were 1 apart from each other, right? Every number was at a distance of 1 from the next number. Here, they're all at a distance of 4 from each other. So the standard deviation is 4 times as big. So 4 times 1.5 is 6. Okay. So that means that standard deviation is affected by multiplication. However, in the previous slide, we saw that standard deviation was not affected by addition. So if we go here, they're telling us that this is new variable y 60x minus 120. The mean is affected by multiplication and addition or subtraction. So we're going to do 60 times 5 minus 120. And if we do that math correctly, we'll get 180. So now we can get rid of choice D and E. They're not right. And the standard deviation would only be affected by the multiplication. It is not affected by subtraction by 120 or adding or anything else. So we're going to do 60 times the 2.3. And you'll notice that I do not need to use the 120 in this case because standard deviation is not affected by addition or subtraction. It is only affected by multiplication. You multiply that, you'll get 138. So that means the correct choice is choice C. All right, so that's the point of those questions. And like I said, if you're listening to this, you'll be able to, I'll put this link up for you later. You'll be able to replay all this stuff for yourself later on. You can also email me if you have any questions as well. Problem 6. At the right are box plots box plots describing the distribution of prices paid for homes in 2 suburbs of Columbus, Ohio. Which of the following statements is supported by the information on the graph? Okay. Part A, both of these distributions are strongly skewed to the right. So strongly skewed to the right would mean that the graph looks something like this. You'd have a small graph, like something like that, and then a really long tail on the right, much longer than the left. So I don't think A is a great answer yet. Maybe it'll be the best answer. Like if I look on the graph, like this looks a little longer than that side, and that looks a little longer than that. I don't know if I would call it strongly skewed. It may turn out to be that that's the best answer, though. So I guess we'll see in a minute. Let's keep reading. The median house price in Dublin. So in Dublin, the median house price, that's where this is. So the median's always in the middle, like that. It's probably like 340,000. Is higher than the 75th percentile of Westerville. So the 75th percentile of Westerville is over here. That's actually true. The median in Dublin is higher than the 75th percentile of Westerville. So that's actually looking like the right answer. Part C says the mean house price of Dublin is $100,000 and then higher than the mean house price of Westerville. So a little word of advice for you. When you have a box plot, any kind of block graph like this, when you have this, like this, and this part here is called the min. This vertical line here is the first quartile. The middle vertical line is the median. This blue line is the third quartile. And out here, this purple dot, this is the maximum. So I think what I want you to realize is for the mean, the average, I don't know where it goes on this graph. These graphs do not give you the mean, they only give you the median. So that's why we can't even answer part C. A is out. Half the houses in Dublin and Westerville cost less than the cheapest 25% of houses in Dublin. If you thought that was true, there's another problem with box plots. Box plots don't tell you how many houses are in each graph. So in other words, the number of houses, this could represent maybe 1,000 houses that were sold in that town. And maybe this graph down here only represents 200 houses sold in that neighborhood. So when it comes to box plots, we are not being told how many houses are in each of those areas. So just keep that in mind. Be really careful with any choice that talks about the number of houses. The range of prices in Dublin is 1.5 times the range of prices in Westerville. Okay, so range by definition is maximum minus the minimum. So the range in Dublin, let's see if we can figure that out. So this looks like it goes from 100,000 is the lowest number. The highest number looks like is about 620. So 620 minus 100 is 520, something like that. In Westerville, looks like the lowest house. Oops, sorry, that's not a good graph. Let me draw that again. And that's even worse. Sorry, my fingers just, you'll have to forgive me. It looks like it's about 50 for the minimum. The maximum looks like about 500. So you have 500, right? Minus 50 is 450. 450,000. So now the question is, if we take 450 and we multiply it by 1.5, do we get 520? Because that's what this is saying. So let's try that out. So I'm going to do here, I'm going to say 450 times 1.5. Let's do the math on that. 450 times 1.5 is 675, right? So that's not the case. That's way bigger than 520. So E is also out. That doesn't work either. Okay, cool. Let's look at this question here. Problem 7. Sample of 250 high school students were asked if you had $1,000 to contribute to one kind of charitable organization, which type of organization would you choose? Below is a two-way table of responses to this question and gender. Okay. Most of the following conclusions seem to, which of the following conclusions seems to be supported by the data? All right, so part A, most of the females who chose a health organization would have chosen an environmental organization as their second choice had they been asked. Okay, so choice A, if you think about it, they're implying somehow that if a female had picked the environment as number one, right? I'm sorry, if they picked the health as number one, so forgive me. That person had picked the health as number one, then they would have picked environment as second. There's actually no way to know that. So let me tell you why. You have 50 people who said I'm female and I think health is most important. We don't know if maybe out of those 50 people, all of them cared about their health and maybe all of them picked either education, aid, or something else as their second most important organization. Maybe for some reason they didn't pick environment as their second. So we actually don't. So choice A, I see how they're trying to trick us with the numbers, but it's actually not true. So A is out. B, there's no association between gender and choice of organization. Okay, so part B, if that was going to be true, what that would mean is that in every case, none of the percentages would change. So for example, sorry about that. I'm just going to find the total of everything. So the total number of people who think education is important is 42. And then for environment, we have 33 plus 29. So we have 62. And then we have 50 plus 28. That's 78, obviously. This next one looks like it's 45. And the last one looks like it's 23. Okay. So if there was no association between gender and choice of organization, that would mean that it wouldn't matter whether you were male or female, you would be equally likely to pick any of the organizations. So actually, I need to do this the other way. I need to add a cross for a minute. So I'm going to do 19 plus 33 plus 50 plus 28 plus 10. So there were 140 females in this survey. And then this is 110 males to add to a total of 250. Okay, so what we're going to do now, I'm just going to pick one category. I'm going to pick environment. Percent of females who think the environment is most important would be 33 out of 140. So if we divide that, 33 divided by 140 is about 0.235. This is percent females who picked the environment as first. That's what that is. We're going to compare that to the percent of males who say the environment is first. There's 110 males, and if we look here, there was 29 here. If we divide those numbers, 29 divided by 110, I'm getting 0.26. It looks like 4. So what I want you to notice that the percent of males who think the environment is important is higher than the percent of females that think the environment is important. So what this is telling me is that males and females think differently about what's most important. So therefore B is out, because if there was no association, these numbers should have been the same. Okay. Part C, the proportion of males who said they would contribute to an environmental organization was higher than the proportion of females who would contribute it. And that's actually exactly what we just proved. I got very lucky there. So choice C is the right choice. None of the students surveyed said they would contribute to religious organizations. Well, categories are education, environment, health, international aid, and other. So other may include religious things, religious organizations. So I can't say that D is wrong. The marginal distribution of organization is 140, 110. So marginal distributions are just the numbers on the outside. So for example, this 110 and 140, that's the marginal distribution of gender. The reason why is because this 140 is telling me there's 140 females, and this 110 is telling me there's 110 males. The distribution along the bottom, that is telling me that's called the marginal distribution, ooh, pen wigged out, sorry. Distribution of organization. What organization are you going to contribute to? Okay, so it takes care of that. All right, this last question is very similar to that. So we're going to take a look at this last question and then we'll be set. And then you'll officially have gone over everything you need to know for your midterm, and you should end up being in pretty good shape. So let's just keep going. Once I'm done with this, I will stop. I'll stop, and if there's no other questions, then we'll end because I need to give you time. Okay. Number 8, do people's opinion of alt rock band Coastal Surface depend on their age? So there's some kind of band called Coastal Surface. I don't know that band. Here's some data to address that question. So part A, calculate 3 conditional distributions for opinion of band, 1 for each group. Okay, so this is super important. Conditional distribution means one row, meaning you're going to look at rows or columns, and they want the conditional distribution of opinion, 1 for each age group. So that's your hint, 1 for each age group. Ready? So the first age group is there. The second age group is there. And the third age group is there. So for each one of these groups, we're going to calculate the percent of people that like, dislike, or uncertain about the band. So let's do that. Ready? So here we go. So for 11 to 14, sorry about that. Super annoying. Okay. So for 11 to 14, the percent that like, ready, would be 18 out of 63, because there's 63 people in total in this group. If I divide those numbers, 18 divided by 63 equals about 29%. So that's who likes it. And then the next group is going to be dislike. And if we try that, we're going to have 30 out of 63. So let's divide that. So 30 divided by 63 equals about 48% of them. So 48% of 11 to 14-year-olds said they dislike the band. And then the last group is uncertain. So these are the people who are like, I don't know if I like it or don't like it. That's what they're saying. So they're I'll just put a question mark, like they're like not sure. Do I like it? Do I not like it? Question mark, question mark. So in that case, according to the chart, there's 15 of those people out of 63. Let's divide that. If you were thinking, can I just subtract the other 2% from 100? You could do that too. So this turns out to be about 24%. Okay, so now we have these 3 percentages are the conditional distribution of the band for 11 to 14-year-olds. That's what this is. So now what we're going to do is we're going to use the same data. We're going to use the next row, and we're going to find the next set of percentages. In other words, for the next group is 15 to 18-year-olds. So let's get those people. Hold on 1 second here. Let me just bear with me for a second. All right, hold on. All right, it's not letting me do that. I don't know why. It's on point. Okay. This program's just a glitchy program sometimes. And okay, so in this next group, I'm going to have to look at the green row. I'm going to have to do 38 divided by 65. So let's do that. Hold on. So here we go. So now we're dealing with the age group 15 to 18. And the percent of people that like would be 38 out of 65. So this is like, we have 38 out of, was it 65? Yep, 65. Let's divide that and see. This number is going to be pretty high, actually. I'm getting 58%. The percent that dislike this group in this age group 15 to 18 is 10 out of 65. There's 10 people out of 65 who are age 15 to 18 who said they don't like it. So 10 divided by 65 gives us 15%. And then lastly, the people who are uncertain. I don't know if I like this band or not. There's 17 of those. So 17 divided by 65. 17 divided by 65 is 26%. Okay, great. Let's look at one more group. We got to look at the 19 to 22-year-olds. Looks like 40 out of 122 like them. So here we go. We got 19 to 22-year-old people. The percent of people that like was 40 out of 122. Let's divide that. I am getting as a percent about 33%. Let's go to dislike. All right, so people who dislike this, there's 67 out of 122. 67 out of 122. Let's divide that. And we are getting about 55%. Then finally, the people who are like, I'm not sure if I like them or not. Who knows? Go back to the graph. I'm seeing 15 out of 122. So 15 divided by 122 equals, let's divide that. And I am getting about 12%. Okay. So those three things, we found the percentage of people who like the band, dislike the band, and who are uncertain about the band for all three age groups. That's what we just did. And the final question of the night is asking us now this. Discuss the relationship between age and the opinion of the band in 2 or 3 sentences. So some things you could say would be, we could say, for example, the 15 to 18-year-olds had the highest percentage of people who love the band. So the 15 to 18-year-olds, 58, it's unbelievable. No, it says it, sorry. 58% of them said they liked the band. Where if I look at, say, the 19 to 22-year-olds, only 33% said they liked the band, right? In the other case, with the, oh, that's not that question. It's over here somewhere. I lost the page somehow. All right, well, oh no, maybe this is it. Yeah, I guess not. Another sentence you could say is, if we look at the 15 to 8-year-old group, 18-year-old group, 26% of them said they were uncertain about this band. They weren't quite sure. But if we look at the 19 to 22-year-olds, 12% thought they were uncertain about it. Okay. The 19 to 22-year-olds, overwhelmingly, the majority of them dislike the band. So that's important to mention too. Okay. And actually, here's the other percentages here. If we look at the 11 to 14-year-olds, the same thing is true there. The highest percent of them, almost half of them, 48% of them dislike the band. So your comment in part B has to be something along the lines of, depending on the age group, the percent of people who like the band, dislike the band, or who are uncertain about the band are different. And therefore, there is a relationship between age and opinion of band. There's a relationship because if you pick a different age group, you get a different percentage of people who like it. So it's age dependent. There's a relationship between the two things. If they had been the same percentages, let's say in every group, 37% of the people like the band, then you would say there's no relationship between age and whether or not you like the band. Okay, so that takes care of that. That's everything you need to know for this midterm. That's the assignments. I will post these notes onto Canvas, as well as a link to the video. It just takes a little bit of time for that video to process on Zoom's end. So you just have to be patient. Take about an hour. All right. Do you have any questions for me before we go?
I have a question, Professor. Since you're going to post the SMAC samples, when do you think that's going to be up by? Because I know the link you have to submit the learning contract is due today.
All right. So I'll extend that date out at least till 2 weeks to the next time, because We haven't talked about that. And that'll
Okay.
give you enough time to look at the SMACs and decide what you think you might want to do.
Okay.
All right. When it comes to SMACs, all of you have like, maybe you working during the day. A lot of you do that. You have access to data, or you think maybe statistics can help you make a decision at work. If you have something like that, you can email me that idea, and I happily either set up a Zoom time to talk to you, or I'll just write you back about what we're going to do. So you might say, for example, I'll give you an example of something happened last time. I had a student a couple years ago, and that particular person worked in a hospital in the food service department, except she managed 2 food service departments. One was for one hospital and one was for a separate building for like a satellite center of some kind. So what she had was survey data from both hospitals. So she knew, like after like I guess once a week, the patients would be asked, how would you rate the quality of food from 1 to 5? 5 was best and 1 was worst. And she had that data for both hospitals, and she had like thousands of data points because they had all these surveys for years. So what we did was we compared the average score on the survey from the main hospital to the satellite building. And we did something called a 2-sample t-test, where you can compare the means of 2 groups and decide if there's a significant difference between those means. So that would be an example of something where people have real data at work, and provided it's non-identifiable. In other words, if I don't know and no one who's reading your paper knows who you're talking about, that we can work on the numbers. So that would be the only other thing I say to you. If any of you do manage to get data from work, you should let your boss know that you just want to look at the numbers only and make sure they approve that. That's number 1. And number 2, there shouldn't be anything identifiable that we can use to figure out who these people are that you're studying. Hopefully that's helpful. That's just one simple example, but there are plenty more to think about that we can do. A couple years ago, also in the middle of COVID, we had a lot of projects related to COVID. There were people working in hospitals who had access to data like who stayed in the hospital for more than a week and whether or not they had had a COVID vaccine. So was there an association between, yes, I had a COVID vaccine, was I less likely to have to spend a week in the hospital? So we were able to answer questions like that based on data that they had collected. None of this stuff's meant to be politically polarizing. We just look at numbers and see what numbers say. All right, so hopefully that's a helpful answer. Any other questions I can help anybody with?
Professor, can I throw out my idea for my SMAC?
Sure, yeah, and actually, if you're willing to do that, that's great, because then I could talk about the whole group, and maybe this will help other people too. So go ahead.
All right, so I work in a hospital laboratory. We have gajillions of data.
I love it.
Particularly, I was going to choose to do look at data about blood culture bottle fill volumes, because that's an important thing. If a bottle isn't filled correctly, it can give a false reading, and then either a patient's put on antibiotics or not diagnosed because it's wrong.
Okay.
So I think look at that and then see if there was a way for a quality improvement side to add to it.
Okay, great. So I'm going to say this first off. It sounds like there's something really good there. So
Yeah.
Let me ask you this question. Is there like an underfilling threshold for these, I guess we'll call these little containers that capture the samples?
The general acceptability is 8 to 10 mLs for the bottle.
Okay.
And we do measure this on a regular basis, and we've been doing it for years, and we've been trying to put things in place to get it to where everybody's always between 8 and 10, but it like gets better for a little while and then it falls apart. So
let me ask you a question about your suspicions. Maybe you have some suspicions. And let's say, so if someone's in the magic 8 to 10, the technician who does the sampling gets this little vial of stuff to you, and it's between 8 and 10. Do you think the test does a pretty good job of being accurate at predicting like the patient's condition?
Yes.
Great. If it's, let's say someone brings in and there's 11 in there, are they more likely to get a negative result or a positive result, or you don't know?
From my understanding, yeah, if it's even 1 ml off, it can be a false result.
And we don't know the direction of the relationship. So like what I'm thinking is this, let's say you're looking for some kind of like a bacterial infection. I don't know what you're testing for.
Uh-huh.
And someone overfills a vial and gives it to you. I was thinking maybe that might dilute the amount, right? Like the amount of detectable bacteria in terms of a ratio to the fluid in there. So if it was diluted too much, then we might be more likely to get a negative result because you wouldn't detect it. Whereas if you had, say, underfilled it, maybe there's not even enough fluid to do the test. I don't know. What could you say about that to me?
I think it's accurate about the overfilling. Underfilling, you might have more there in the bottles. There's already, media that mixes with the blood. So if you underfill it, you'll have more media than you have blood, and you won't get the right reaction either.
So I think we could do, here's what I'm thinking about for your study. This is what I like. So as a lab, you receive a bunch of vials of these little containers that have the fluid in it, 8 to 10 mils, hopefully, with the sample, and you're going to test it. So here's would be something I would think would be a good idea for your project. I think you might even like it. What I would like to know is let's look at all the samples, or a large number of samples where where they were ideally filled between 8 and 10 mLs, as you put it. Let's calculate in those among those vials, what percent of those vials gave a positive result. So let's say, we look at 100 of the, let's say we find out that of the vials that were correctly filled, 72% of them indicated a positive result for whatever you were testing for. Okay. Then let's look at vials that were underfilled and calculate the same percentage. So what you would do in that case is you look at all the underfilled vials and calculate what percent of those underfilled vials came back with a positive test result. And what we're going to test to see is if the proportions are the same or different. And that's called a 2-proportion z-test. We would, as researchers and people who designed this test, they wanted it to work between 8 and 10 milliliters. We would think that the 0.72 I mentioned is probably the correct proportion of sick people. And if we looked at the underfilled vials, maybe we were getting a higher number. And if we were getting a higher number, we might think, okay, that's a consequence when you underfill these things, where our percentage is going up. And that means you're overprescribing antibiotics probably, because there's a higher percent of those patients who are going to get prescribed antibiotics, and you're contributing overall to antibiotic resistance. So I think that would be, how do you feel about that project?
Yeah, that sounds good.
I love it. I find we'll do a lesson next time where we talk about, I have a cool idea. I think I talked about it before. I put a link to it about Bayes' theorem and COVID testing. So, and it really, all that mathematics applies to exactly what you're doing. It's really cool. Can I ask you a different question?
Yeah. Sure.
When my kids are a little bit older now, when they were younger, if I went near a doctor's office, maybe other people in the meeting here could think about this. I went near a doctor's office. The doctor would say, "Oh, they have a sore throat?" I'd say, "Yes. Let's test for strep." They wouldn't ask me any other questions. Now, when they did that, and I don't want to sound cynical, but that induced an extra copay with my insurance because typically, you get the $25 copay for the visit. Then you might pay another $5 because you had some kind of, or whatever it is, maybe it was less than that. I don't know. And then they also billed the insurance company for an additional service because they were running this test. It seemed to me like that's not a good idea unless my son, for example, not only does he have a sore throat, but maybe he's had the sore throat for 3 days and it's gotten worse. Maybe he's feverish. Maybe he feels weak. And with those 3 questions, answers are yes, then he's probably more likely to have strep throat. But if he just has a sore throat and no other symptoms, maybe it's not a good idea to test for it. So the question I was asking, which could be interesting, would be,
Yeah.
it would be neat if, let's say you have this data going back, say, I don't know how many years you have it going back, but here's another question. Let's say it went back 15 years, and maybe 15 years ago, the percent of people who tested positively was like 90%. And maybe today, like 15 years later, the percent of people who tested positively is only 60%. And the
Mhm.
reason it's happening is because we're testing way more healthy people than we used to. You know what I mean? Like that's sort of an interesting,
Yeah,
interesting thing to happen. That's another idea if you decide you don't like the other one.
yeah,
Okay.
that's definitely, yeah, that, that makes sense. And there's certain tests
Yeah.
that we
Yes.
look for like overutilization of,
You
for
actually
things
do
that
that,
are
huh?
not necessarily needed.
Yeah.
But like blood cultures are specifically if someone is like, they suspect that they have an infection in their blood specifically that might lead to like sepsis or something of that nature.
It sounds to me like you're dealing with kind of a specialized test where it's not just like at the whim of a doctor's office. It sounds like you'd have to request this kind of test. It's more involved to do. That's what it sounds like, right?
Yes,
Right. Okay. Great. Hopefully, how do you feel? A little better?
yes.
Good. Does anyone else have a question like that they want to discuss? Thank you for that question, by the way. I think that's helpful to all of us.
Yeah, thank you for helping me.
Oh, absolutely. Absolutely. All right. So I'll do this. Yeah, Regina, is that you?
Yeah, because I was going to say, like my job is very, very private. I don't know how to get information from them.
Oh,
Oh,
don't worry. We could do
I don't know
something.
if I'm sorry.
Yeah, we could do something different too. Like we could do a project based on something you personally like where we can get public data.
Okay.
Yeah. Yeah. So that's
Yeah,
no
because
problem.
my job was like, okay, because I had to do a smack before I did it. It was like pulling teeth because they're very private.
Yeah. No, a lot
I
of
just need
jobs
some
are.
ideas. I'm trying to get some good ideas. I'm trying to think,
All right. So here's what I would recommend to all of you, and that's why I'll make this like that submission for the learning contract 2 weeks from now, is that spend the next week, get your midterm done, make sure you feel good about that. Once that's done, Regina, anyone who wants to, email me and I will give you some ideas if you're stuck. If you don't know how you want to, what kind of smack you want to do, I can help you do that. My main goal with the smack is this, that you get to use some of the statistics that we learn about this year, this course, this semester, that is, in a way that you might find helpful or interesting. Like it could be about something you do at work. It doesn't have to be that. Maybe there's a question you've always wondered about that we can answer with statistics, something like that. You name it, all kinds of things. If you're interested in real estate or something else, we can look there. There's plenty of data there that we can look at. Percentages of foreclosures, are they really increasing over time? Right now, if you're paying attention to the economy at all, you'll notice that the inflation rates are high. We probably all notice that, and it's not making anyone really happy. And it's not making me happy, I can tell you that. We might have something there where we can look at some data, and maybe as the interest rate the government proposes goes up, what markets seem to be most sensitive to that. So for example, supposedly there's going to be a decline in the prices of new automobiles, but there's lots of public data we can look at to test and see if that's true. Okay. All right. So I'm going to stop there. I'm going to say I wish you all the best with the midterm. I will post. So I got to make a little note to myself here to do this. So I'm going to post these notes. I'm going to post a link to the video of this session. And then I'm also going to post a link to sample smacks. That will all be on Canvas by the end of tonight, tomorrow morning, the latest. Okay. All right. So I'm going to say this. It was a pleasure talking to you.